All right, Mr. G Math coming at you live, room 7202. November 2nd. Volumes of solids, of revolutions, discs, and washers. This is the last lesson in this unit. This unit fully connects to what you just did. It's not like we're going to do something brand new. The part of your brain that got scratched is going to be scratched more. It's not going to be a different part of your brain. We're still finding volume. But this time we're going to find volume by rotating a region around an axis or a line. And if you rotate around a line or an axis, the shape when you do a cross-section is actually going to be a full circle. And the word they use for a full circle is a disc. Can you picture a disc being a full circle? So before, the known cross-section was actually flat and then came at you at your nose. This one goes all the way around. It's not flat on the page coming at you, all the way around. And when you cut it like a loaf of bread, the shape you see is a full circle. Not a semicircle, a full circle. And then in this, the word they use for a full circle is a disc. So obviously the formula we're going to use for a full circle is pi r squared. So that's the intro here. Let's see. If for a given base you create a semicircle cross-section that's sticking toward you and away from you, you've created a full circular cross-section. Since the formula for area of a circle is pi r squared, the formula for the volume with the circular cross-section is this. And notice how they keep practicing. Where does pi put? In front, right? That constant. In front of the integration. I need you to keep practicing that. You get comfortable. And if it's perpendicular to the x-axis, what coordinates we're going to use? X, right? And if it's perpendicular to the y, we're going to use the y. Okay, so warm-up example. So use the region bounded by y equals x squared and y equals negative x squared. And it goes from x equals 0 to y, x equals 0 to x equals 1, shown in the graph. To create a volume by using circular cross-sections perpendicular to the x-axis. So I need you to picture the full circle that's here. If you cut it, there's a full circle. So if I take it all the way from the top to the bottom of the graph, that would be the diameter. If I go from the top to the bottom, that would be the diameter. But I want the radius. The good news is it's actually way easier to write down the radius than it was the lesson before where you had to go 1/2, right, the diameter? Because half the diameter is the distance from the x-axis to wherever that is. Meaning the actual y-coordinate from the x to the y-coordinate is what I'm looking for. I'd have to double that to find the full diameter. So when I find the y-coordinate, that is the radius. When I find the y-coordinate, that is the radius. And I need that. And that's easier than what we did the lesson before where we had to go 1/2 the diameter. We don't have to do that half to create the radius. All right. So we're going to integrate from 0 to 1. The formula again is pi, what? R squared. And what does y equal in terms of x? I circled it. Done. Okay? Yes, you could write that as x to the 4th, and then you could integrate it by hand if you need to. But that's the setup. In some ways, the setup for a disc, and then we're going to talk about a washer, which is like a donut, has a hole in the middle of the washer. In some ways, it's easier than what we did last one, where you have to think of formulas for a triangle, a square, a rectangle, all that. We're only looking at circles, and if you let it be, I think it'll be a little bit more basic. We will if it's required. So you'll see when it's required in a moment. So circular cross-sections can also be formed by revolving very thin, essentially no width rectangles about an axis of revolution. These circular cross-sections are more commonly called discs. So if you rotate around a line and you cut that by rotating, what shape is formed by rotating, right? and if you cut, you'd see the circle, right, that it formed. It doesn't have to be on an axis. You can rotate on the line y equals 2 or something like that, but you'll see that example. So do you see the formula for the disk, which is pi r squared? And when would it be dx? When it's perpendicular to the x-axis, and dy when it's perpendicular to the y-axis. Okay, let's look at example number 1. So set up an integral for the volume of a solid revolving around the region y equals x squared. And we have y equals 0, which is a fancy way of saying the x-axis, and x equals 1. So that region is going to be rotated around the x-axis. Because it's being rotated, what's the cross-section? A circle. What's the formula for a circle? Pi r squared. And what I need to know, it is about the x-axis. So if it's about the x-axis, we're going to use the x's. What are the bounds? From 0 to 1. And then inside would describe the radius of this being rotated. So can you see what I see here will be the radius. If I rotate it, you'll have a bottom part too, right, that would rotate around it? Yeah. I just want the radius. So in other words, it's only what y is will describe the radius. And what does y equal again? It's exactly what we just did for the warm-up, right? Done. Example number 2. Find the volume of a solid formed by revolving the region in quadrant 1 bounded by what? Y equals x squared, x equals 0, and y equals 4. So x equals 0 is a vertical line that is a fancy way of saying the y-axis. That's x equals 0. Y equals 4 is a horizontal line. And then y equals x squared, of course, is a parabola. What are some points I can put here? And 0, 0, right? All right. I'm not going to draw the full parabola because it's been bounded with x equals 0. Can you see this region? This region is going to be revolved around which axis? The y-axis. So can you see the circle that would be formed around the y-axis? My bounds have to be with what letter? The y-axis. If you're overthinking it, we got to wake up. Y, right? What's the lowest y? What's the greatest y? So it goes from 0 to 4. The formula is pi r squared. Correct? And it's in terms of what letter again? So what do I need to know is what describes the radius. So what letter will be in here? Y. But in order for y to be in there, you need to know what x equals so I can plug it in. Right now I know y equals x squared. So can you tell me what x equals? Yay! So what will I put inside here? And notice it's bounded by what? So in other words, if it was bounded by a different line, we'd have to go right, subtract, left. But when we subtract 0, does it affect that root x or root y? So what goes inside here? It says find the volume. That means we're not done. It didn't say set it up. It said find it. So can you see pi r squared? What would I do? All right, I can do this. You can do this. Root y squared is just what? What is y when you integrate it? Y squared divided by 2, or 1/2 y squared, and we're integrating from where to where? Notice I just put the pi in front with parentheses. I don't have to sweat about it. What number do I plug in first? Oh, I heard that on the video. That was a big yawn. And then what number do I plug in? In this case, when I plug in 0, the answer is 0, so I need to subtract 0? No. So simplify it, and what's your answer?
85.
Beautiful. Done. Okay? 2 days ago, this was impossible. Today, after learning, right, and not giving up on yourself, not impossible. Turn the page. Washer formula. That's correct. Some of you actually know what a washer is, right? It's what you put your clothes into. It's actually also, because the English language has different things that mean different things. Sometimes when you have a project at home, you need to put a washer with a screw because otherwise the screw would go right through something. So the washer allows it to, it looks like a steel little donut. And they come in different sizes. Go to Home Depot one day and ask where the washers are. You can go there, and then when you go to the washer and dryer area, then you go, no, I mean the other washer. So it looks like a donut. In other words, it's a circle and a circle, right? There's a hole in the circle. Okay. In this case, we're going to have an outer radius and inner radius. And the importance is that if you take the outer radius and subtract the inner radius in terms of the circles, what you're left with is what you need. You have the big circle, which is pi r squared.
Will that just be the diameter?
No. So, if you take the big radius and find the area of the circle, take the small radius and find the area of the circle, what's left over is what I want. The big circle, find the area of the small circle, and then when you subtract it, what's left over is what I want. Okay? That's what I need to understand. You have a big circle, you have a small circle, and when you subtract the big circle and the small circle, what's left over is the actual volume I'm looking for. The big circle, subtract the small circle. Big circle, pi r squared. Small circle, pi r squared. Put it together, factor out the pi, and can you see how we get what we get? Whoa, there it is. So big circle, pi r squared. Small circle, pi r squared. When you subtract the two, that's what's left over that I need. And when you factor out the pi, can you see the formula that comes from that? Again, if you don't, we're just setting up the learning, right? If I asked you to find the area of the shaded part in here, what would you do to find the area of the shaded part? You would find the area of the outer circle, you'd find the area of the inner circle, and then subtract the two, and what's left over is the area I shaded. If that's confusing, you've just got to give yourself time, and don't be stubborn about it. So that's the formula that comes from it. The big radius squared, subtract the small, right here when you factor out the pi. So let's look and see how that works. Look at example 3a. Set up the integrals. We're not finding the volumes. Revolving the region of the parabola is what? And then what is the line? Y equals 0. So y equals 0 is a fancy way of saying the x-axis. And then the parabola. I want you to notice that if you revolve here, this would not create a disk, washer, but would create a disk. Did I say? Yes. The washer is when there's a space between the region and what you're revolving around. If you're revolving around a line and it's right up against that line and you revolve it, it's solid. If there's a space, a gap between what you're revolving around, when you revolve, what's going to happen is it's going to create a hole with that gap. Okay. Well, what's the setup for A? And it's the x-axis, so from where to where? 0 to 1, pi r squared. What describes the radius is the y value, and the y is equal to negative x squared plus x. The y coordinate at all time describes the radius, and y equals that. But this is going to be different. See, that's a disk. A washer. Do you see the gap? I'm revolving it around the line y equals negative 1. Do you see there's a gap there? A space? when I revolve around that line there, there's going to be a space in the middle. That space in the middle creates a washer, a donut. So what's the formula we're going to use? Well, we're still going to integrate from 0 to 1. We still have a pi in front. But now it's the big radius squared minus the small radius squared. So what's the big radius? So that's the one from the outside. If I go from the line all the way to the top, what is the top there? What describes it? This parabola, which is what? So negative x squared plus x, and then I have to subtract top, subtract bottom. What is the top and the bottom? This is 1. So when you subtract 1 or subtract negative 1, it means the same as. So I'll put in there subtract negative 1. That describes the outer radius. So the outer radius is the top, subtract the bottom. Subtract. That was the big radius. What's the small radius? What do you see this line right here? What number is that? 0. What is the radius of the small circle? From what number to what number? And when I go top, subtract bottom, what number do you get? Positive 1. And that's it. It's the top radius or the big radius, subtract the small radius. How did I find the big radius? Top, subtract bottom. How did I find the small radius? It's the part underneath, subtract bottom. Again, top, subtract bottom. Okay, let's look at it again. You're going to learn this when you practice through the assignment. But right now we're setting it up. So what little parts do we know right now? I'm integrating. From where to where? What x value? 0 to 1. We can do that. You realize that there's a gap between the line I'm revolving around and the actual area, correct? That gap means it's going to be a washer. So it's going to be pi, but then we're going to have the big radius and the small radius. All right, do you see the line we're revolving around? Take that line and go to the bottom of the region. Can you do that? All the way to the bottom. Top, subtract bottom. What number is the top? What number is the bottom? So what's 2 subtract 0? Okay? So the big radius is 2, and the area then would be pi r squared or 2 squared. Okay. What would describe the smaller radius? So I take the top of the line and I go to the top of the area. The line I'm revolving around to the top of the area I'm revolving around. What describes the smaller radius is the equation. What's the equation again? And the top number is what number? 2 subtract what? So it's 2 subtract, what am I subtracting? Negative x squared plus x. All of that together squared. Top subtract bottom. So again, if I wrote it underneath here, maybe it'd be a little bit neater. 0 to 1. The first radius was what? 2. The second radius was 2 subtract negative x squared plus x. dx. All right, let's try number 4a. Set up integrals for the volume of solids formed by revolving the region bounded by y equals x squared and y equals x plus 2. So do you see y equals x plus 2? Do you see the parabola y equals x squared? We're revolving it about what? The x-axis. So when you look at the x-axis in the region, is there a little gap between the two? So do we have a bigger and a smaller circle? Okay. So it's going to be pi what are the x bounds? From where to where? -1 to +2, right? Okay, I need an expression for the big radius, and I need an expression for the small radius. So put in parentheses and square it so you can organize your brain around this. All right, the big radius goes from where? Okay, what line am I revolving it around? Okay, go from there to the very outer part of the region. Do you see that? From there to the outer part of the region. What do you notice? What's on the outer part of the region? X plus 2. And the bottom is what? 0. What's x plus 2 minus 0? X plus 2, and then we're going to square it. So x plus 2 describes the outer radius no matter where we go along the line. Okay, start again with what I'm revolving around, the x-axis. Now instead of going to the outer part of the region, we're going to go to the beginning part of the region. Do you see that? What describes the beginning part of the region? And top subtract bottom would be x squared minus 0. And x squared minus 0 is x squared. And you set up an integration to find that volume by revolving around the x-axis. All right, one more here, B. And then your work is when you're going to learn it. Now what are we revolving around? Do you see where y equals 4 is? It's right here. Is there a gap between the line and the region? So there's going to be a big circle and a small circle. The setup, pi, integrate. From what to what again? -1 to 2. And we have a large circle and we have a small circle, dx. So what's going to describe the big radius? Okay? So do you see the line that I'm revolving around? Go from there and go to the bottom, furthest away from what you're revolving. That's the big circle. Can you see that radius right there? What is top subtract bottom? 4 subtract what? X squared. Can you see how I did that? Top subtract bottom. Okay, what describes the small radius? Start at the line you're revolving and then go to the top half of it. Do you see that? That's the small radius. Again, top subtract bottom would be what? 4 subtract, and what's the line? And use parentheses. And that's it. That is the setup. And that's what you type in your calculator. All right, note. We'll end here. When finding volumes using either discs or washers, you should always sketch your region and draw a representative rectangle. That's that line, right, that I did with the arrow? Your figure will help you decide whether to use dx or dy. The figure can also help you choose a method to find limits and to decide what's top and what's bottom, what's the big radius and what's the small radius. Your integral must be consistent. All x and dx and all y and dy. I don't know if this is helpful. Perpendicular. I don't know if that's helpful. But whatever. Mr. G Math over.